Today, let's go into something a lot more current. Let's go into what a neural network is. So a neural network, you've probably seen illustrations like this, something like bunch of circles connected to each other and having like couple of layers, and then all of them accumulate in some output layer here. So you've seen this illustration probably somewhere in some icon, some image, but really, what does it mean? Why does it look like that? So today, let's go into the topology of a neural network. Let's talk about what it is, how it works, how it learns, and how it predicts things in the future. So let's start with this thing in itself. As I said just now, there is an input, there is an output, and there is some layers in the middle. These middle layers are called hidden layers because when you pass something into the model, it just comes out, and normally you don't think about these layers in the middle. So they're called hidden layers because you don't think about them. Now that's the overall topology, but what is each of these circles? What is the thing that the model, the neural network is doing? What is the neural networks? Each of these circles is a neuron. You might think of neuron as the thing in the brain, like, oh, I learned in biology that there's this dendrite, there's a cell, and then there's the axon, whatever, and ooh, this is biology. But no, this is a biological neuron. What we're using in computers today are artificial neurons, otherwise known as perceptrons. Perceptrons are basically very similar to an artificial and biological neuron. Yeah, it's very similar to biological neuron. In fact, you can draw it almost similar to one. So you can draw it like this. I've seen the illustration, it looks kind of like this. So it's x, 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 and then you have a function, and then you have more functions. I think it's sigmoid, and then yeah, something along the line, something along the lines of this. So what this is you take a whole bunch of inputs. These are x. You can see it's x1, x2, x3. There's a linear function on it, so you know your math is y equals to mx plus c. Instead of mx plus c, it's x1 plus c1 plus m2 plus x2 plus c2, and etc. So this is a linear function in math, and you know that through a linear function you can combine multiple variables to get a single output variable. And this is another function is called an activation function. You don't need to think about that now. Just know that this activation function introduces non-linearity. So instead of having your entire neural network be all linear functions, these activation functions can kind of enable or disable some, such that the entire model isn't just one big linear model. So then this is the output, and then this goes out, and this is the value you want to get. So we've covered what one perceptron is. So one perceptron, you can think about it as a single neuron in the model. So within this perceptron, within this neuron, how does it learn? So to break things down, let's have the simplest perceptron ever. We have a single x variable. Let's call this a bias variable. So it's like y equal mx plus c. You pass these two into a function f, and then you get the result here. So let's say output, yeah. So at the start, your model doesn't know anything. So let's say you're trying to predict a function, because again, the purpose of a neural network is just to model some data. So let's say you give it some data, it's literally y equals x. This is the graph. So you have to start the model with some randomly initialized weights, because it has to start somewhere, it's to randomly guess some relationship, and so this way it will guess the relationship between the output and your inputs. So let's say you know y equals x. Let's say I pass x equals to 1. You predict y. You're supposed to get y equals 1. However, the model itself has some weights. What are weights? Weights are your gradient term basically in a linear equation. So in this case, we know y equals mx plus c, and this allows, so let's randomly start off these m and c variables, because we don't know what they are, to be let's say 0.66 and 0.3. By the way, in case I confused you, this c shouldn't be c. It should be a constant term like 1. This allows the model to, you know, kind of implement c in a way. I'll tell you why later. So y equals mx plus c, it guesses that, and so let's say we pass in 1, it will predict a value of 0.66 plus 0.3. Wait, that's actually the correct answer. It's close enough. So let's say, oh, the model is lucky, it guessed, oh, 0.96. It's very close to 1. And so that's pretty good, but there's still a difference somewhere. This difference is known as so the difference in your predicted value, which is equals to y hat, is equals to the predicted value. This predicted value minus the true value is your error term. So in this case, 0.04, and we know whether it's positive or negative 0.04. So again, from this intuition, let's say you tried to predict a line that's y equals mx plus c, but let's say you predicted something too high, or maybe you predicted something too low, or maybe it's the wrong direction entirely. Then in this case, you would know that it's the wrong direction, and hence you can try to correct it towards the correct direction. I hope you get it, intuition. But basically know that the direction, and like, you can, from the values and the error, you can kind of tell what's going wrong. And so using calculus, my favorite calculus, I'm very bad at calculus, I'm not gonna try to do it on camera, but you can use calculus, it's called back propagation, to calculate the error term. So to draw something out, back propagation would be something like dy over d, let's say we want to get a term x. So this is the gradient of y with respect to x. Basically, how does changing x change y? We want to shift x into the direction where it can more accurately predict y. And as such, we're trying to find this gradient of y with respect to x so that we can shift it in the direction we want. So overall, think of this as, this is called back propagation, and through this back prop process, we can adjust the weights of the model to be more accurate and predict the output that we want. Now back to the thing about 1 just now. Why did I say 1 and not c? Well, if you kind of think about it, y equals mx plus c, it's sort of a special case of y goes to mx plus, it's sort of equals to m1 x1 plus m2 x2, except for x2 is actually just like 1. So your c constant term can be really just a set input 1, and then you can tune the m2 value here itself. Yeah, so that's why I put 1 there. So far what have we covered? We have covered this structure of a neural network, how does input and output, how it's inspired by a biological neuron, and how using math we can actually get this thing called a perceptron, which works kind of similar to a neuron. So where are we now? How do we get to this function here? Let's draw it a bit bigger. Let's get 1, 2, 3, 1, 2, 3, 1, 2 inputs, and let's say 1 output. So I'm too lazy to draw off the connections, so just let's say it's something like that, blah blah blah, and here. So this is the input. Each of these input neurons actually, each of these input neurons receive your input variables x1, x2, etc. Normally put them in a matrix, but let's just not involve matrices. And the outputs of these, let's say they are y1, y2, since there's only 2. These are passed into the second layer as their inputs. So this layer will receive maybe y1, y2 as the inputs, and they'll generate, since there's 3 of them, they'll generate z1, z2, z3, etc. This goes on, this goes into here, which goes into here, and this gives out a final y hat. This shouldn't be y, but this is the final y of the entire model. The entire model gives you this y value, which is the prediction of this output y value from your inputs x. And each of these nodes, as I've said just now, is the perceptron equation that we've seen on top. So these perceptrons, they come together and they're able to form this larger model. As I said just now, by right in maths, if you do this with just linear equations, it will actually converge to just one single linear equation. So no matter how much mx plus c you put in there, it will all just sum up to just one y equals mx plus c equation, unless you put an activation function like this sigmoid here. Just to illustrate, a sigmoid activation function will look something like, so let me just draw this here. This is an activation function. Some of the graphs look like, let me draw things. It may look like this. This is a sigmoid curve. Let me make it look nicer. Some of it looks like this. This is called ReLU, or rectified linear unit. This is called a sigmoid. Yeah, so you have sigmoid, you have a ReLU, and you also have, and let's just say you didn't do anything. This is just your normal linear. So this activation function converts this linear into one of these functions. The benefits of so are quite varied, but the main benefit is that it won't just be a combination of linear equations, and when you put some of these activation functions in, they can produce a non-linear function in general. So if you, yeah, I won't go deep into that. So that's basically as deep as I want to go today. You've learned that you've learned to understand kind of what this diagram you've seen everywhere looks like, what it actually means. It's a bunch of interconnected perceptrons that can work together to predict an output from an input. This, one final tidbit, this is normally called a multi-level perceptron, because, surprise, surprise, it's a multiple levels of perceptrons. So hopefully you've learned something from this, and let me know if you want to go deeper into this explanation.